On Monday, a paper came out in the journal Physical Review Letters that describes what may be the strongest material in the universe. It's called nuclear pasta. It's found inside neutron stars, the supermassive, dense remains of stars that have gone supernova. They are, in fact, made mostly of neutrons. We've known about nuclear pasta for a while, but we haven't really understood its properties until now. And while it probably won't be the next big building material, it could help astronomers understand how neutron stars behave. In general, neutron stars are pretty wild objects, and so as a result, their anatomy is also pretty wild. For one, they have brittle crusts, which we've known about since the early 1970s, shortly after these stars were discovered. The crust is formed by neutrons that are forced into a crystal lattice by the star's extreme gravity. A pretty cool consequence of that brittleness is that the crusts break if put under enough strain. And crust breaking can cause all kinds of behavior, like an increase in rotational speed and magnetic outbursts. Just beneath that outer crust lies the nuclear pasta, which was first proposed in the 1980s. This material is formed when, at high pressures, the star's neutrons and any surviving protons are compressed so much that they start organizing themselves into some really odd structures. For example, they form these long strings called spaghetti and these board-like shapes called lasagna. And for the record, those are both the technical terms. Scientists are great. For a long time, though, we've really had no idea what it meant for neutron stars to have nuclear pasta. Apart from the weird shapes and the general composition, we didn't know much about its characteristics. Like, if the crust can break, can the pasta? In an effort to figure out what was going on down there, a team from McGill University, Indiana University, and Caltech ran the largest supercomputer simulations of this material. They tested it under all kinds of stretching and strain, trying to get it to break. And it turns out it needed a lot of strain, like more than it would take to snap any other material, making it potentially the strongest stuff in the universe. This pasta layer might also influence how the crust above it breaks. That means that when astronomers get data from a neutron star's crust, they might be able to extrapolate what's going on in the pasta below. Of course, this is the only simulation of its kind that's been done so far, so there should be more news to come as scientists perform similar tests. In other news, earlier this month, scientists reported that they observed matter falling into a black hole. Now, that in itself isn't remarkable. That's how black holes work. That's kind of their deal. But these observations show matter moving at a really weird angle and super fast. And that's what makes this news. Matter collects around black holes in massive accretion disks, where the innermost matter can sometimes fall in. All our models of black holes and basically all our understanding of how they gobble up stuff assume that their accretion disks orbit with no tilt. They're like big rings parallel to the hole's equator. Except there's no physical reason that needs to be true. Accretion disks could have any orientation. We had just never seen a black hole behaving like its disk wasn't parallel until now. In this new study, published in the monthly notices of the Royal Astronomical Society, a team studied a black hole at the center of a galaxy almost 1 billion light-years away. They used data from the European Space Agency's XMM Newton telescope, a space telescope that mainly observes things using X-rays, which black holes emit tons of. Specifically, the group was looking for the fingerprints of certain elements. These fingerprints appear as patterns of lines in an emission spectrum, and each line is associated with an element emitting specific wavelengths of light. If an element's pattern appears shifted from its usual wavelengths, that likely means it's moving, and scientists can use that difference to calculate the speed of the material. In this case, the stuff falling into the black hole was moving around 30% the speed of light. And if you think that's fast, you are totally correct. It's significantly faster than what we usually see from this kind of matter. What was maybe stranger, though, is that this stuff appeared to be falling directly onto the black hole, not spiraling inward from a disk like we usually see. Turns out, based on earlier simulations, this is exactly what you would expect if the black hole had a tilted disk. See, disk tilting can cause some instability, and chunks of the accretion disk can break off and separate from the rest. And those chunks can collide and cancel out some of each other's rotation. And without all the spinning, the matter is pulled directly into the black hole way faster than normal. Thanks to simulations, we thought that this so-called chaotic accretion might be pretty common for supermassive black holes, but we'd never seen it happening. After all, accretion events are pretty brief, so we'd have to catch a black hole at just the right moment. But now it looks like we've finally done it. Of course, we'll have to do more studies to confirm these results, but this is a big step forward in black hole research. And it's always kind of nice when our simulations seem to be right. Thanks for watching this episode of SciShow Space News, especially to our patrons on Patreon. You help our team get access to the latest papers as well as film and edit all this cool research, and we couldn't do it without you. If you'd like to help us keep making episodes like this one, you can go to patreon.com/SciShow.